Hi everyone, welcome back. This example 811 is actually kind of a practical application of the last example that we did, which was conceptual. The last video segment was a conceptual problem, kind of about a golfer, and here we have sort of the same thing. We have an object sliding across a frictionless surface. All right, this surface is frictionless right here, so let's think of it as like an air hockey table or something, with the exception of a rough patch right here, which takes energy out of the system. This is our non-conservative work that is done right there. So we want to find the distance of this, the amount the spring needs to be compressed in order such that we know the velocity of this sliding box after it hits the rough patch. All right, it'll all make sense in just a minute. We are going to apply our conservation of energy principles, but the reason this is a lot like the golfer problem is because there's no potential energy involved. There's no up or down. It's simply kinetic energy and then friction working against it. So that makes it a little bit easier for us. Okay? Well, let's start by writing down all of our knowns. That our K constant, our spring constant, equals 730 newtons excuse me, per meter. We know that the mass of the block, M, equals 1.2 kilograms. All right? And our distance, D. Okay, D is what we're solving for. D is unknown, so we want to solve for that. Let's see. You know what? I'm not going to call that D. I'm going to call this X. I'm going to call this X. I'm going to cross this out right now because when we compress a spring, I'm not just Xing that out, but I'm actually making it X right there. We're going to call that delta X. When we compress a spring, we say that the compression or the work that is done to the spring, or the potential energy that the spring has, is, we say what? That's 1/2 kx squared, right? So let's call that X. So X is what we're solving for. But we have this distance here that the sliding block slides over, that that friction takes work out. Let's call that D. All right. So our distance that the spring is compressed is X, but our rough patch. So the distance of our rough patch, just as a reminder, that's 5 centimeters, which is 0.05 meters. Okay? Lastly, we have a coefficient of kinetic friction of the rough patch, and that's 0.44, and there are no units for that. Did we miss anything? Oh, final velocity. We'll just write it in the middle. Final velocity of the block after crossing the patch is 2.3 meters per second. Okay, so there's a lot going on here, or at least it seems like it is. Initially, we have energy. I didn't mean to do that. We have energy that is put into this spring. Okay, the spring then propels the block into motion. All right, so all that energy is turned into a moving block right here. But then it crosses this rough patch and it slows down slightly, and so we have a final velocity of 2.3 meters per second, which we should assume is going to be less than the initial velocity coming off of the spring right here. But even though there's a lot going on, we can still mark an initial energy and a final energy. So the initial energy of the system right here is going to be marked there, and the final energy of the system is going to be right here. And this rough patch is going to represent the non-conservative work that is done. Okay? You know, I kind of mistakenly said, not mistakenly, but accidentally said that there's no potential energy. There's no potential energy due to gravity, but we are going to find out that at the outset, at the very start, there is going to be potential energy, and you probably picked up on this, but it's going to be in the form of spring energy, not gravitational energy. Okay? So, all right, let me take this and I'm going to shrink this down a little bit. And I'm going to do this. Okay, still see everything? All right. Well, like we always say, we say that the initial energy of the system, energy initial, I'm sorry, I start with final. Well, it doesn't really matter. Energy final equals energy initial plus accounting for whatever non-conservative work is done to the system. Okay? So, the final energy of the system. Is there any more potential energy in this anymore? Has it gone up any distance? No. Has it compressed the spring? No. So, potential energy, U final equals 0. But what about kinetic energy? Well, there is kinetic energy, right? That's going to be 1/2 mv final squared equals, what's the initial energy of the system over here? Is it moving at all? No. The kinetic energy initial equals 0, so it's not moving yet, and all the energy is in the form of potential energy. U plus U initial. Of course. U initial. What is the U initial? What is the potential energy? Well, that's our 1/2 kx squared, right? The potential in the spring is 1/2 kx squared. And by the way, that x is what we're solving for. Plus 1/2 kx squared. Now, I ran out of room, so I'm going to write below right there. Or maybe I'll just kind of dogleg down here. All right? We're not done yet because we have our final energy of the system, our initial energy of the system, all wrapped up in that potential energy of the spring. But we need to account for the non-conservative work that is done. So the non-conservative work that friction does right here is going to be what? Well, it's going to be mu k times mg, right? It's going to be our friction force, mu k times mg times the distance. That's why I changed that this 5 centimeters to a distance right here. That's the work that the friction does. And of course, friction is always negative, and so I didn't leave much space right there, but I'm going to put a little minus sign right there. There we go. That accounts for our non-conservative work that friction does. Okay. I think rewriting this, it'll make it a little bit simpler, because some of these things are going to be dropped out. Okay? So, let's see if I can fit all this in here. 1/2. You know what? Again, you guys can't see this, but I have this menu bar on the far left that prevents me from writing near to the edge. I'm going to drop all the way down here. All right. So 1/2 mv final squared. That's our final energy of the system. Not a very good square. Let's fix that. V final squared equals. Again, there's no final potential. There's no initial kinetic, so that goes away. So equals 1/2 kx squared plus this non-conservative work that friction does, plus negative mu k mg times the distance, which is what, 0.05 meters. All right? We are solving for this x right here. We're solving for that distance. How much was the spring actually compressed originally? All right, well, let's just go ahead and solve for this. Let's see, this minus sign in the parentheses would make this plus negative, but if we want to get all this to the other side, we're going to have to add it to the other side. All right, does that make sense? So we're going to go 1/2 mv final squared plus mu k mg times the distance of that rough patch equals 1/2 kx squared. Okay, we're getting there. It'd be great if we could cancel out all these 1/2s, and we can by just dropped my stylus. We can by multiplying everything by 2, but that means there has to be a 2 out front right here. All right, this doesn't have a 1/2 in front of it, so there has to be a 2 that comes out front. So we're going to cancel that, and put a 2 out front. So that's going to be, it's going to have a 2. And we're also going to divide everything by this k right here. That's going to come down. So it's going to look like this. mv final squared plus 2 mu k mg d, all divided by our k constant, our spring constant, equals x squared equals x squared. Well, we don't want x squared, we want x, right? So how do we get rid of the squared? We're going to square root that. So I'm just going to do that in one operation as well. So I'm going to put a square root over this whole thing right here. And that's going to be our equation for how far this spring was originally compressed, well, before we let it go. Okay, let's just simply plug in our values, and we should get it. So the mass is 1.2. 1.2 times the final velocity, that is 2.3 squared, right? 2.3 squared plus 2 times our coefficient of kinetic friction, that's 0.44. 0.44 times the mass, 1.2 times 9.81 times our distance. Oh, I'm going to have to squeeze down a little bit more. There we go. Times our distance of that rough patch, and that was 0.05 meters. 0.05. Extend that. Meters. Okay, numerators are accounted for. Let's do the denominator. The denominator is easy. That's just our K, which is 730 newtons per meter. That's quite a top-heavy fraction right there. Well, this is going to allow us to solve for our displacement of our spring. And I get that our displacement of the spring is going to be 0.097 meters. All right, so that is 9.7 centimeters that spring is compressed. All right, and all this was gotten simply by taking our the final energy of the system and the initial energy of the system, and accounting for the non-conservative work that was done. We didn't have to break this up into all kinds of different little parts. We just simply knew that at every part of the system, all energy was conserved until the point at which it was not conserved. So we could say that the beginning energy was going to be constant all throughout until after the rough patch, and then the final energy was going to be that much less than the initial energy. So we started with our 1/2 kx squared. We ended with our 1/2 mv squared, which is kinetic energy, and the difference is the non-conservative work done by friction. So, good application of the use of the conservation of energy. Sorry, I kind of blanked there for a second. But dealing with non-conservative work that is done. All right. So, thanks for following along. I'll see you on the next one.